All right. Well, hello and welcome everybody to the Sentinel Innovation and Methods Seminar Series. My name is Richie Weiss from Brigham and Women's Hospital in Boston, and I'll be moderating today's session. So just to give a little bit of a background, so the U.S. Food and Drug Administration Sentinel system helps to address questions related to the safety and effectiveness of marketed medical products. The Sentinel Innovation Center focuses on developing innovative methods to further advance Sentinel by leveraging new data sources, building new tools, and enhancing real-world evidence capabilities through advanced analytics. And so the Sentinel Operations Center focuses on supporting FDA in the use of the Sentinel Common Data Model and associated modular programs or tools to gather evidence to support regulatory decision-making. The Sentinel Operations Center maintains FDA's active risk identification and analysis, or ARIA system. So we launched the Sentinel webinar series to engage experts and innovators in key areas related to the Innovation Center's master plan and operations center's methods work. And so with that, I am pleased to introduce today's speaker, Dr. Xiaojuan Li. So Dr. Li is a pharmacoepidemiologist and instructor in the Department of Population Medicine at Harvard Medical School and Harvard Pilgrim Healthcare Institute. Her research interest is in generating valid and actionable evidence regarding the uses, benefits, and harms of medical treatment from real-world data to inform clinical decisions and healthcare delivery. Dr. Li has expertise in large electronic healthcare databases, advanced pharmacoepidemiologic and causal inference methods, and comparative effectiveness research. She has extensive experience in the use of high-dimensional electronic health data, including administrative claims and electronic health records to assess effects of complex treatments. So the title of her presentation is Inverse Probability of Exposure and Censoring Weights for Marginal Structural Models. And so before we get started, I'd just like to mention that your lines are muted throughout the duration of the presentation. So if you'd like to pose a question, please type your question into the Zoom question and answer feature, and then we will answer questions at the end of the session. Finally, this session is being recorded and will be made available through the Sentinel webpage, which can be found at the website sentinelinitiative.org. So without further ado, Dr. Li, thank you so much for joining us, and I'll turn the time over to you.
Thank you, Dr. Weiss. Can you hear me okay? Okay. Thanks for that very nice introduction, and thanks for having me here. For today, I'm going to talk about inverse probability weighting. This approach has been increasingly used for effect estimation in observational research. I hope with today's really high-level introduction to this approach, you'll get to appreciate more about the simple idea behind this approach for causal analysis of observational data, and begin to recognize potential applications of this approach, as well as having a better understanding of special considerations needed when applying it. This will, again, serve as a really high-level introduction. I will include some resources for more technical details if for those who are interested. So in observational comparative effectiveness research, we aim to provide evidence regarding the benefits and harms of treatment or intervention to inform clinical decision-making. So we're always concerned with this valid causal effect of some kind of treatment or exposure A on an outcome of interest Y here in the simplified DAG, or directly a cyclic graph or causal diagram here. Please know that throughout the presentation, I'm going to use treatment and exposure interchangeably. But due to the observational nature of studies, there is potential bias due to confounding, which makes the exposure groups not directly comparable. Many methods exist to help to control for this type of confounding. For today, I'm going to focus on inverse probability weighting and show how this approach can work not only in time-fixed setting, but also in the complex time-varying setting when time-varying confounders are themselves affected by prior treatment, for which the convention method may yield biased estimates, even when there's no residual confounding. Here's the outline of this talk. As I've mentioned, my goal here is not to go into the technical details, but rather try to give you a flavor of what inverse probability weighting is and how it solves the problem of confounding control. First in the time-fixed setting, and then in the time-varying setting. There are a few references and resources throughout the slide and also in the back of the slide that can dive deeper into this. I will also try to include a discussion regarding the opportunities and considerations we need to have when we apply this method in observational research. So the origin of inverse probability weighting can actually date back to 1952 when it was first developed for survey sampling. What we wanted to, when we wanted to do inference from a selected sample from the population to the population, if there's differential selection exists among individuals with different characteristics, the ordinal sample quantities such as mean or proportions are likely to be biased estimates of their corresponding population quantities. So weighting was developed and can be used to weigh those oversampled individuals down to create a sample with no differential selection. So they will look more like the population. Thus, you can see that weighting is basically a way of standardization to look like the population where the sample was drawn from. So it's a very common method that we adjust for confounding in epidemiology. And when we are interested in comparisons between groups, such as in our studies of comparing two different treatment options on the outcome of Y, because the distribution of some factors may differ between the two treatment groups, the direct comparison of outcome risk in the two groups may not reflect the true treatment effects on Y. So what we do is to try to remove this distortion by this factor L by controlling for it. Standard methods such as matching stratification or regression adjustments can be used to adjust for this L. It's reflected on this DAG. Basically, we're putting a box around L, which blocks the path from A, L, Y, and then the effect will recover will be only through from A directed to Y. Inverse probability weighting can also achieve this confounding control by basically creating a pseudo population in which the association between the treatment and measured confounders is removed, which is equivalent of removing the arrow between L and A. So using this the standardization language, inverse probability of treatment weighting basically reweight each exposure group to look like the entire observed study sample, so that will share the same covariate distribution. And depending on the type of weights you use, the standard population for this standardization is different, such as for the very commonly used inverse probability treatment weighting, the standard population is the observed population. And to help you visualize this, so after applying this inverse probability of treatment weighting, we'll end up with a weighted sample or a so-called pseudo population comprised of two groups, both sharing the same covariate distribution as the observed, the entire observed study population. So now after weighting, we'll have one group all treated and one group untreated. And they're the same people, and then we can then estimate the treatment effect had the entire population been treated versus the entire population being untreated, which is the average treatment effect or ATE. If we can assume that we have adjusted for all confounding through weighting, then we can use this measured risk ratio to estimate the desired causal risk ratio. So how does the weighting approach accomplish this or work exactly? Let's work through a very simple example together. So I have this very simple study of effectiveness or safety of 2 different types of bariatric surgery. And having type 2 diabetes as a confounder here. So we have a total of 14 individuals in the study. 6 of them have diabetes, so the orange colored on the left, and then 8 people without diabetes, and the blue colored on the right. In this population, you can see the prevalence of having diabetes is 6/14, which is 43%. And then within the treated group of the 6 individuals, 4 with diabetes, so the proportion of diabetes among treated is 4/6, which is 67%. But within the untreated group of the 8 individuals, 2 had diabetes, so the proportion is among the untreated is 2/8, which is 25%. Now you can see there's imbalance of diabetes distribution across the 2 treatment groups in this study sample. And to try to make the treated group just like the overall population, we want to have 6 diabetics and 8 non-diabetics. And to do that, we need to weigh each of the 4 treated diabetic individuals by 6/4, which is basically the 1 over the probability of being treated if having diabetes. Each treated non-diabetic individuals will be weighted by 8/2, which is 4. So for each individual, again, the weight is the inverse of the probability of having the observed treatment value given the confounder L value. We'll do the same for the untreated group, while the untreated diabetic individuals each receive the weight of 3, which is 1/2/6, while the untreated non-diabetic individuals each receive a weight of 1.33. So with this inverse probability treatment weight, we created a pseudo population of 28 rather than the original 14 we started with. But now we have 14 people with everyone being exposed or treated, and 14 people untreated or treated with the other option. They are the same people, and they have the same distribution of confounders, diabetes, as in the entire observed population, which is 6/14, which is 43%. Remembered in the original observed population, there was imbalance between the 2 groups with regard to diabetic distribution, which is 67 versus 25%. Now, also they differ from the population distribution, which is 43%. After weighting, now we have this pseudo population, both diabetic proportion in the treated and untreated were the same as the total population as 43%. So that's exactly the reason why we say IP weighting methods reweigh each exposure group to just look like the entire study sample with this treatment weight here. So now with this weighted sample or pseudo population, we can just estimate the treatment effect on the outcome by setting up a 2x2 table and counting how many individuals in the treated has the outcome event and how many in the untreated has the outcome event, and then get the risk to calculate the effect measure of interest or risk difference or risk ratio. As you can see, the implementation of inverse probability weighting estimation is quite simple in this point treatment setting. To summarize, basically we first need to model the exposure as a function of the confounders or covariates, and then we then need to assign each individual in the data a weight of the inverse of probability of having the observed treatment value given the covariate value L. We'll then obtain the effect measures of interest in a weighted sample or the pseudo population. And please note that the individuals with the same confounder L may not have the same weight because the inverse probability weights depend on the observed treatment values as well, which is different from the propensity score, which I'm going to get to next. And as you may have already have been wondering, and then you also recognize that the denominator of the inverse probability of treatment weight looks just like a propensity score. So confounder, with the confounder summary score we commonly use in pharmacoepi study or comparative effectiveness research. The propensity score is the probability of being treated given the covariate. So for treated individuals, their inverse probability of treatment weight is actually just 1 over propensity score, while the weight is 1 over 1 minus propensity score for the untreated. Remember, the inverse probability weight is the inverse of probability of receiving the observed treatment, not receiving the treatment or the exposed, the one. So there is a very close connection between inverse probability weighting and propensity score, especially when we try to use the weighting approach for confounding adjustment after estimating the propensity score. There are also many other applications of propensity score for confounding control, including matching and stratification, which, however, doesn't share some of the flexibility of the weighting approach that we'll get into in the next section on time-varying treatment. So after weighting, we first did a 2x2 table to do the effect estimation. Instead of doing that, we can also fit a model to the pseudo population or the weighted population for effect estimation. So here with the model, we impose an additional assumption and with this marginal structural model. So often this is marginal structural model considered as a tool for longitudinal time varying exposures, but they can also be used in the time fixed point exposure setting. So basically, we try to control for all confounding through weighting and then using a weighted model without covariating it to estimate the parameters of a marginal structural model. So we can use a weighted logistic model to estimate the parameter of a marginal logistic model and a weighted Cox model to estimate the marginal structure Cox model. And if the weights adjust for all confounding, we say that the parameter of the weight model estimate the parameters of a marginal structure model. And if we can sufficiently adjust for all confounding through weighting, we'll estimate a marginal effect because the outcome model actually doesn't have any variables in it. So we estimating a marginal effect instead of a conditional effect. By also attempting to adjusting for all confounding without controlling for covariates, we can also avoid for this potential bias through controlling for time varying confounder, which I'll get into that shortly. So now we can see basically the inverse probability or the inverse estimation of marginal structure model. This is basically a multivariate extension of a standardization approach that has been commonly used, and that uses the total observed population as the standard population. Just want to add a little note there. So what do we mean by marginal structure model? What's marginal? Marginal basically means that it's the marginal distribution of the counterfactuals or the potential outcomes that's being modeled. And it is called structural, meaning that we're interested in the causal. And so we're having a model for the potential outcomes, but instead of for the observed outcomes. And a common issue with inverse probability weighting is the treated individuals with very low propensity score, or the untreated individuals with a very high propensity score will end up with with extreme weight. That will potentially make the weighted estimator unstable, resulting in wide confidence interval and reduced precision. So one way to do this is to use stabilized weight, which is basically multiply the weight with the marginal probability of observing the observed treatment without conditioning on any of the confounders. So the numerator now of the weight is basically this probability of the observed treatment instead of 1 in the unstabilized weight. One nice feature of this with stabilized weight, this preserves the sample size, while the unstabilized weight doubles the sample size. And we can also use this feature to check for the distribution of the weights to make sure the weights are well behaved. So they have a mean of 1 for the stabilized inverse probability weight and treatment weight, and 2 for the inverse probability of so 1 for the stabilized inverse probability treatment weight, and 2 for just the unstabilized weight. And alternatively, when we have larger weights, we can also reassess the propensity score model and try to identify positivity or near positivity violation. And we could do it by try to trim the non-overlapping propensity score region before we calculate the weights, or we can also truncate the weights. By truncating, I mean by setting the weights that's greater than the specified threshold to the value of the threshold. Say if we want to truncate weights at 20, so any weight that's at above 20 will be assigned the value of 20. So as we have established in this time-fixed setting, the inverse probability weighting is equivalent to this well-known epidemiological method of standardization. If you will, you can also think this approach as simulation method to see what if everyone is treated and what if everyone was untreated. This approach can achieve appropriate adjustment in the presence of time-varying treatment setting, so can extend to this longitudinal setting, which we're getting here now. And I want to note that there are many different ways to implement inverse probability weighting of margin structure model in the time variance setting, but all of them will share the similar implementation steps. So we'll first process the data by weighting, and then use the weighted regression for effect estimation. Okay, before we get to that, let's first see what complications this time-varying treatment and confounding bring in this longitudinal setting. And in real-world studies of medication or other type of treatments, time-varying is very common. We have a lot of time-varying exposures, and especially when we're dealing with chronic conditions such as hypertension, diabetes, or HIV infection. So when people are treated for a long term, their treatment may vary, and sometimes their treatment also may be adjusted based on their evolving clinical characteristics. So with that, we'll have time-varying treatment, and we'll also have time-varying confounding. And in many cases, there also will have time-varying confounding that also themselves being affected by the prior treatment. So basically, we'll have time-varying confounding that both confounders and they're also intermediate So as you can see that in this example here, if we're looking at treatment of intravenous iron among hemodialysis patients, you can see that the anemia parameters at time M is both a confounder for iron treatment and the mortality outcome, but it's also being affected by iron treatment in the last time point. So with this, if we want to estimate the effect of this time-varying iron treatment on later mortality in the presence of this time-varying confounder, a common approach or the standard regression approach is to actually fit a model by including the confounders as independent variables. With this approach, actually, because this variable is here, we have two arrows pointing into the red arrows here, pointing into anemia parameter, and this is called a collider. And then by condition on the collider, we'll actually open a backdoor path, basically inducing an artificial association between this iron treatment and this unknown or unmeasured hemochromatosis variable. So here, if we don't adjust for this anemia parameter, we're going to have residual confounding in the effect estimation. If we actually include this in the model, we would lose part of the treatment effect that's mediated through this anemia parameter. And we also will induce this artificial association, which is called framed as also a selection bias by inducing this association between the treatment A and the unmeasured confounder. And this would occur even in the absence of the unmeasured confounding or without model misspecification. So fortunately, inverse probability treatment estimation of marginal structure models can appropriately adjust for this complex time-dependent confounding without these issues. Loosely, this IPW estimation approach reweigh subjects in the analysis to try to create a pseudo cohort and mimic a situation in which the assignment to iron treatment is at random. So basically, the time-varying confounders are not associated with the future exposures. And then without this confounding in the pseudo population, we can then just do a crude or unadjusted analysis in the pseudo cohort, just like what we did in the time-fixed setting. And that will provide an unbiased effect of the exposure if we don't have any unmeasured confounding. So can see this IPW approach can adjust for confounding and also selection bias. So can this two things at the same time. In this time-varying treatment setting, we estimate the weights using time-varying treatment weights, and this the standard inverse probability of treatment weighting. Sorry. So we'll estimate the time-varying weight, and the standard inverse probability of treatment weights for each patient is basically the inverse of a probability of receiving actual or observed treatment given the prior treatment and covariate history. And so it's similar like what we did with the point treatment, but now we're going to estimate the probability at each time point. So here I give in first the standardized weights, and basically just informally the first step is to try to estimate the treatment at each time point as a function of previous treatment and history of covariate. And it can include both time varying and baseline covariates. And in the second step, we'll use the probability of observed treatment at each time point. And this is done by subtracting the estimated probability of treatment at each time point from 1. And in the next step, the cumulative probability of observed treatment is calculated at each time point. And so this estimated probability at each time point, they are multiplied together. So to try to create a weight, because as you can see, we're estimating weights across different time points, and this weight can be highly variable. So they can be either very small or very large. And this could, when there is a violation of positivity assumption. So to try to account for this, these weights can be also stabilized. And this is done by multiplying the weight with the cumulative probability of actual treatment, conditioning only on the baseline value of the covariate V. So you can see there's a V in the numerator. And in our numerator, we're not going to include any time varying or time invariant. We're not going to include any time varying covariates. So with this approach, we will get the weights called stabilized weights, and compared to the unstabilized weights, they're less variable and less skewed. In the simplest case, this is basically try to emulate a population while there's a sequential treatment in patients instead of treatment. So this is emulating a population where the sequential treatment in rows who are not treated is random, conditioning on the baseline confounders and treatment history. And in longitudinal studies, some participants are lost to follow-up throughout the study period for some reasons, including factors related to the treatment or to a competing event. This will influence the results if there is a systematic difference between those that are lost to follow-up and those are remaining in the study across treatment groups. And also the reasons for leaving the study is related to the outcome. So when we have this type of censoring, we call it informative censoring. This can be also viewed as another form of time-varying confounding because the probability of censoring depends on the outcome the subject would have had in absence of the censoring. So in marginal structural models, we can also use inverse probability weighting to deal with this, which is by adding a type of weight called censoring weight in the estimation process. Basically, we want to recreate a population that would be seen without dropout, without censoring. The censoring weights can be used to control for the real censoring, like the loss to follow-up, administrative censoring, or dropout, etc. And the same set of weights can also be used to address for non-adherence or non-compliance if we're interested in estimating the effect of sustained treatment. This type of censoring is often termed as artificial censoring. And the derivation of the weights will follow the similar approach as the treatment weight, except that now we're estimating the probability of being censored or remaining uncensored if we're interested in them staying in the sustained treatment. So once we get the censoring weight and we also the treatment weight, we can then multiply the weights together in order to obtain a joint IPW to create a pseudo population that has all this confounding removed. This is basically, it will be the inverse of joint weighted, it will be the inverse of the joint probability of observed treatment and also remaining uncensored. So if you try to imagine that pseudo population, that will be a population in which there's a random treatment allocation with respect to risk of outcome, and there's no loss of follow-up on conditioning on baseline covariates and the treatment history. Under the assumptions we're going to outline later, the parameters of this marginal structural model are equivalent to the estimate of the weighted model fitted in observed data, which we refer that to as the outcome. And for whether the IP censoring weights or IP treatment weights or the combined weights, the practical process of fitting this weight is the same, apart from the kind of outcome model fitted. So as you can see, when we try to stabilize the weights, we actually include the baseline covariates V in the numerator model. And because we do that, that means there's still confounding due to these variables, and then we need to include this V variables in the outcome model. So that's a little different from what we have seen in the time fixed setting. And because the weighting process induces dependence between observations from the same subject, so a robust variance estimator is needed, or we can use Bootstrap to account to get the effect the variance. There are many opportunities to use the IP weighted estimation of margin structure model to estimate a more clinical relevant question. That's including continuous treatments on the risk of outcome, or the sustained when we are interested in the sustained treatment effect, the non-adherence needs to be dealt with, and we can use IP censoring weights to handle that. And we can also evaluate different dynamic or treatment strategies, or if we're interested in initiation versus no initiation when there is time-varying indication involved. So there's many opportunities to apply this. I want to mention there's one particular approach to implement this weighting, that is to use this three-step clone-censor-weight approach to estimate the effect of treatment duration on survival outcome. This basically what it does is first, if you have multiple strategies or different treatment durations you are interested in, we first we define the strategies and then make copies of the original data with one copy for each strategy of interest. That's the clone step. And then we'll artificial censor observations when they first deviate from the index strategy. That's the censor step. And then in the next step, we'll use weighting to adjust for the potential selection bias induced by artificial censoring for strategy deviation. Then we can do the effect estimation using the weighted. So this three-step approach actually can estimate the effect of treatment duration from observational data without the common bias when we naively compare between long-term versus short-term users. And this can be also used to compare any treatment strategies that are sustained over time. So Like regression, the validity of the estimates actually rests on several assumptions. So try to link the estimates from what we get to the causal effects. We actually require this following assumptions, and we can only take our estimates as seriously as we take the conditions that are needed to needed for us to actually get for this estimate to have a causal interpretation. These conditions include exchangeability, which is also known as unmeasured confounding, and consistency, which is treatment version irrelevance, and positivity. And we have no measured error. So treatment status will be measured accurately at all time points, and also the predictors of the treatment and outcome are also measured accurately at all time points. And there's no model misclassification, so we have all the weight model need to be well to be well specified. And basically, what this assumption does is without any of this, because we lack data on distribution of the confound or the potential outcomes or counterfactual outcomes in the data, we won't be able to go from the observational data to causal inference. But we try to assume these assumptions, and if they are approximately met, they will allow us to identify and try to make causal inference. So however, there are several limitations of inverse probability of marginal structure model weighting that first, we can only achieve balance on the measured confounders. And the exchangeability assumption is not verifiable. And this approach is very subject to positivity violation, which will result in unstable weights. And also result in wider constant interval. However, this approach has a very big advantage of will be able to adjust for this time varying confounding without suffering from this Collider stratification bias we first talked about. And this approach is also quite simple. So it's a standardization of creating the pseudo population. So it's very easy to explain. And there's also, because we're only interested in the treatment model and sometimes censoring model, then there's less computation and also less model to specify. And because it's the sensitivity to positivity violation with this approach, it's also easier to identify positive violation when we use this approach compared to another approach, which is called the parametric G formula. And here, just trying to introduce to you that IP-weighted marginal structure model is one of the set of G methods. All this method is trying to do is to estimate the G formula. So G formula is according to Jimmy Robbins that the counterfactual outcome, mean or risk associated with some user-specified time-varying treatment or treatment strategy can be written as a G formula, which is basically a particular function of the baseline and time-varying data. And so with this formula, when we estimate the contrast in this function of the different treatment or treatment strategies, this can generate unbiased estimates of the causal effects. So all this IP-weighted marginal structure model or parametric G formula or TMLE or W robust estimation or some other ML maximum likelihood estimation are trying to estimate this G formula. So IPW is just one type of estimator for this. So we have established that the IP-weighted marginal structure model is equivalent of the standardization and can be used to control for confounding and selection bias in both time fixed and time varying setting. It can also be used to deal with this really complex time varying confounding that involves this treatment confounder feedback loop. So I hope this can be applied more, but then also let's consider what special considerations you need to think when trying to implement this approach. So like I said, this inverse probability treatment of marginal structural model that will allow us to recover the treatment effects even in the presence of complex treatment confounding feedback loop. This will allow us to actually provide evidence on a lot of more clinical relevant research questions to try to inform treatment decision. And depending on what you do, IP weighting can be also used to either address sampling bias or generalizability bias. So if we are estimating the weight of being selected into a study population, or if we're estimating receipt of treatment or exposure, then we are trying to control for confounding. If we want to actually weigh to estimate the probability of having observation at a visit, we can also use this to address or missing data, and also to address for censoring. So there are a lot of applications of this inverse probability weighting that approach that we can see applications in our research. But when we try to implement this or apply this method for observational research, I would ask you to start think about first to try to define your research question, to think about what exactly the intervention you are interested in and the treatment effect you are trying to target, and also how does that align with a real world clinical decision. Secondly, you want to think about data and also the variables, whether you have all of them. First, what kind of variables you need to try to recover this true effect. So we can use causal diagrams to try to identify this relations between the variables and what kind of variables you need now, be time varying or time fixed. And then lastly, you need to, this actually a very important one is to think about the data, whether you have the data to allow you to do this kind of analysis. So basically, because we saw the IP-weighted approach that can only be valid when we have no unmeasured confounding. So because you can only balance on the measured confounders, then you need to think about what important variables are associated with either the treatment, the indication, or the censoring and discontinuation, whether they are all measured in the data or not. So this is kind of a quick summary of the components of the data you may need to have here. So around treatment and all the confounders and outcome. And when we are doing this studies using the databases that we have for research, most of the time administrative data, we need to evaluate whether the data is fit for this purpose. In administrative data, we may have proxies for the indication of the treatment initiation well measured, but we may not have all the determinants of non-adherence or non-compliance measured. Now we need to think whether we'll be able to capture that data from another data source, hopefully with more data and linked data and comprehensive data around the patient journey become available, we'll be able to have more data fit for this type of purpose. And also want to think about the measured error that you may encounter in database studies when for the type of databases that I use a lot, claims data, a lot of time we have dispensing data. Then how do you define discontinuation or adherence? And there's this very possible of misclassification of that variable, and especially the date of the discontinuation. How do you define that? Basically, operationalize this is challenging, and hope this also needs to take into consideration. And also, in a lot of the methods, the regular implementation of that assume this regular interval, but within the real world clinical practice, most of the time, the visit process is actually not within the equal intervals, and there's also this different monitoring for different people, and there's time varying monitoring, which also needs to be taken into consideration when we are evaluating this. And again, there's also model misclassification and the positivity violations you need to think about. With all these challenges, I want to say when you have the appropriate data and also well-defined question, this approach can help you recover the treatment effect, and it's really versatile. So hopefully I have convinced you to see that IP weighting is basically a standardization approach. So you can create the pseudo population, allow us to evaluate the effect. And this approach can be used even in the complex setting of time varying setting, and can estimate the causal effect of treatment in that. And if you're interested for more reading about the technical details, there's this workshop listed on the top, and there's also the reading that you can go into try to get the deep technical details of this. And with that, I hope you can include this in your toolbox, and then consider that when you try to use for your research.
Great. Well, thank you so much, Dr. Li. This was a really terrific presentation. So we now have a few minutes for questions. Again, just as a reminder, your lines are muted. So if you do have a question, please type it in to the question and answer box, and I can go ahead and read those. And so we already have one question from the participants that says, can we use IPTW for HDPS, meaning the high dimensional propensity score, instead of normal PS? Sorry.
Oh, sorry.
Yeah, that's okay. I was going to say, I don't think we can hear you. Yeah.
I just realized I was on mute. Yeah, I think basically the IPTW here is the treatment weight is basically try to evaluate the probability of having observed treatment given the covariate, and in the setting. So when you use high dimensional propensity score or propensity score, what we're trying to do is to get to evaluate the treatment probability. I think you can use that. I haven't used it myself, but I think there is a possibility to use that as well.
Great. And as we're waiting for more questions to come in, I had a question as I was listening to your presentation. And so when you were talking about, the application of inverse probability weighting, you talked about the application of it for the point treatment setting where we have a fixed follow-up time and we're not worried about time varying confounding, and then the application of time varying weights to account for time varying confounders if we want to evaluate dynamic treatment regimes. So when we're applying IPTW in the point treatment setting, it's pretty standard to evaluate covariate balance across treatment groups, as a diagnostic to let us know how well our model is fit, how adequately we're controlling for confounding. So in the time varying setting, is there some type of equivalent to that, some type of equivalent diagnostic? Because it seems like, there's a lot of potential for model misspecification as we're multiplying weights together, especially if we're also using inverse probability censoring weights on top of time varying inverse probability weights. Is there some type of diagnostic that researchers can apply to check if their models are well fit or they're adequately balancing covariates across the treatment groups?
That's a very great question. First of all, I don't know kind of a quick, simple way or diagnostic to my knowledge, which may have been there, but I haven't seen that myself. I think there are other ways that the model misspecification that can be assessed. A lot of times in fitting all of this inverse probability treatment weights, a lot of times we kind of evaluate by looking at the treatment, looking at the weight distribution, and by assessing that by assuming several different models and see the distribution and to see which one is better behaved than another. And then we normally use the better behaved one for the primary analysis and the other sensitivity analysis. But there's another way to do this is to actually evaluate using a different G method. Like I mentioned, we have a parametric G formula, and there's also TMLE. So there's also doubly robust estimation methods that are available. What the general recommendation is, because these different methods, they have different assumptions, and also they use different models. So maybe you can try to fit several different approaches and see how results agree with each other, and because they may be subject to different model misspecification. But I hope there'll be simple diagnostic for this time varying covariate distribution. But I will see. I think there's one that I'm not positive on, but I might seen one that was attempting getting that, but maybe I can get back to you when I check into that a little bit further. But in my practice, what I have done, we generally don't do more of a diagnostic for that.
Yeah, great. Thanks, Dr. Li. So we're just about out of time. Just as we're about to wrap up, a bunch of questions started coming in. So I apologize to everyone if we're not able to get to your question. But I'm sure Dr. Li would be open. If you have questions, you could reach out to her directly through email. We'd just like to once again thank Dr. Li for this really terrific presentation. As a reminder, this session has been recorded and will be made available through the Sentinel webpage. You can also find details and registration links for future Innovation Center and Methods seminars on the website, which is sentinelinitiative.org, all lowercase. And this concludes our session. So we hope to see you next time. Thank you, everybody.
Thank you.